thank you for the invitation to speak at the workshop. And thank you everyone for being here for my talk. I wish I could have been there in person, but oh well. So today I want to talk about a fairly recent project with Andrew Fourier and my mentor at McMaster, Cam Frank. And I think the preprint may have just shown up on arXiv today, so it's super fresh. So I'll start the talk with a lot of facts that you probably know. A lot of people so far as I've seen have talked about at least some congruence subgroups. But basically the general idea of the talk is that we will generalize this idea of congruence subgroups to phi congruence subgroups, where phi will be certain representations. And then we'll see that that generalization makes sense. And then we'll also show an example of one such family of phi congruence subgroups, and we'll talk about some of the modular forms. Okay, so the principal subgroup of a congruence subgroup of level n is known to be the kernel of this very natural homomorphism from SL to Z and to SL to Z mod n Z. Okay, and based on this definition, if you're looking at it, then you can see that gamma of 1 is the whole modular group. And then, obviously, since we have a kernel, gamma of n is going to be normal. And in fact, a lot of you have probably done this exercise when learning modular forms. The map is a surjection, which means that the principal congruence subgroup has finite index. Okay, another way to think of this principal congruence subgroup of level n is that you get matrices that are congruent to the identity modulo n, right? So 1, 0, 0, 1 modulo n. Based on this, we can define a whole lot of congruence subgroups to be those of finite index that contain gamma of n for some n, and the smallest such n will be the level. Okay, so we've seen already gamma naught of n, I think in at least 2 talks in the past couple of days, and it's those matrices that are congruent to 0 modulo n in the lower left corner here. Okay, well, the theory for congruence subgroups is fairly well understood, and you can meet them in a lot of different theories. So first, well, not necessarily first, but one of the places where you meet them is to think of the action of a congruence subgroup gamma on the upper half plane by Mobius transformations, okay? So for example, an element in the upper half plane maps to, okay, so an element tau maps to A tau plus B over C tau plus D, where A, B, C, D is a matrix and some congruence subgroup gamma. And then modding out by that action, you end up getting a moduli space for elliptic curves with certain level structures. Another, well, not necessarily disjoint place, but congruence subgroups then give us the theory of modular forms. And that's a very rich theory. A very cool elementary application of modular forms that a lot of you probably know about is we get finite dimensional vector spaces over C, which means that you can get very nice relationships in terms of the divisor function, right? I think that's one of the first elementary applications of modular forms. But of course, modular forms are definitely more far-reaching than just these elementary identities that we can get just from the finite dimensional vector space property. And then furthermore, we can generalize congruent subgroups to arithmetic subgroups of algebraic groups, which gives us the theory of automorphic forms. But of course, these are just some of the places we can meet congruent subgroups in the wild, so to say. Well, it turns out that, in fact, a lot of the finite index subgroups of SL to Z are not congruent. In fact, most of them are what we say non-congruence. Okay, so just they're not congruence, non-congruence. I know, very original. And there are a lot of good reasons to study non-congruence subgroups. Okay, so why would we want to study them? Well, first, as some people say, don't fix what's not broken. A lot of really cool things happen for, in the case of congruence subgroups that also work for non-congruence subgroups. For example, you also get finite dimensional spaces of modular forms, okay? And the moduli space interpretation also works for non-congruence subgroups. In this case, we get elliptic curves with certain non-abelian level structures, as William Chen showed in his PhD thesis. So some things work similarly, as in the case of congruence modular forms, but a lot of things are also very different. So the unbounded denominator conjecture, now a theorem that was proved very recently in 2021 by Caligari, Dimitrov, and Tang, states that if you have a modular form for a finite index subgroup of SL2Z that has integer Fourier coefficients, okay, then it must be a modular form for some congruence subgroup. That kind of thinking the other way around is that if you have a modular form with rational coefficients to the point where the denominators in the Fourier expansion get larger and larger, okay, so you can't really multiply by any large integer. You can multiply the whole modular form by some very large integer to get just integer coefficients. That's what it means, like the unbounded denominator property. Then what you actually get is a modular form for a non-congruence subgroup, which is pretty cool. However, just because this conjecture has been proven doesn't mean that there aren't still some questions to answer. So for example, what do we know about the primes that show up in those denominators? Can we say more? And in the example that I'm going to talk about today, we can actually say a lot about the those unbounded denominators and what primes show up in their factorization. Another thing that works very different for non-congruence modular forms is that we do not have Hecke operators. Okay, so Hecke theory is very important for the theory of congruence modular forms. And in fact, if you're looking at the action of the Hecke operators, you get certain recurrence relations among the coefficients of the new forms. For non-congruence modular forms, you do not have Hecke operators. However, you get a very interesting phenomenon. You don't get a recurrence relation, all right? But instead, you get some very interesting congruences. So the Fourier coefficients of some special modular forms satisfy some interesting congruence relations that are reminiscent of the recurrence relations that happen in the congruence case. Okay, so there's some very interesting phenomena that happen for non-congruence modular forms that still need to be studied. Okay, so given this, we still have a lot of questions to answer. So there's a few things that would be helpful to have. One part of today's talk is generalizing congruence subgroups, okay, to a new kind of class dependent on certain representations. And these phi congruence subgroups that I'm going to introduce soon will actually contain classical non-congruence subgroups, okay? And the other thing is it would be potentially useful to have a lot of examples of non-congruence subgroups, and we'll give one interesting family. All right. So I'm sorry about all the text here. I'll tell you but let me tell you what the general idea for phi congruence subgroups is. You start with a homomorphism into a linear algebraic group, okay? And then because the full modular group SL2Z is finitely generated, that means that where T and S get sent to can't look too bad. Okay, so you'll still, have potentially some primes that might divide. You might have T sending to elements that contain some sort of elements in an extension of Q. But the idea is that eventually you get the image is contained into the OK 1 over m points of the algebraic group. Okay, so OK is the ring of integers of some number field. And then because of the denominators, you can kind of bunch them all up together into some m, integer m. Okay, so you end up with a map to these points. And now you can take reductions modular integers co-prime to m. So that's the general idea that we're going to look at. We have a homomorphism, and I'm going to kind of call this a representation, okay? Hopefully you'll forgive me for that. And then I'm going to take modulo either primes or integers co-prime to m. Given this, we will define the phi congruence subgroup of level n, where n is co-prime to m, to be those elements that map to the identity modulo n. Okay, so you have this phi, and then you have a reduction happening here, modulo n. Okay, so hopefully you can see that this is very reminiscent of the principal congruence subgroup. Okay, in particular, if you take phi to just be the map from SL to Z into SL to Z, right, just the identity, and taking that modulo n, you get that the principal congruence subgroup is just gamma phi of n for phi equals the identity. Okay, and then generally a subgroup, we'll call it phi congruence if it will contain this principal phi congruence subgroup for some n. All right. I'll show you some facts that hopefully will convince you that considering this class makes sense. All right, so here's just kind of the definition. Okay, if you're taking phi, gamma of phi 1, you get the whole modular group again for all those homomorphisms. Of course, you kind of end up with a kernel, so each gamma phi of n is normal and of finite index. And then if you have an n1 dividing n2, then you have a natural inclusion. And I think here n2 and n1, okay, yeah, makes sense. I think in a previous iteration of the talk, I had them flipped and there was a bit of a contradiction there. Okay, and there's still a couple of more properties that show you that these phi congruence subgroups kind of play nicely with each other. And that's kind of what we expect for congruence, for just the classical kind of congruence subgroups. Okay, so now that we have this kind of generalization of congruence subgroups, I want to turn to an example of a family that will turn out to be phi congruence, and then we'll study that family. Before I define this family, are there any questions? I'm not sure if there's questions showing up in chat. I'm not seeing it because I'm having the full screen. So
don't worry, I will see the question in the chat.
Okay, excellent. Thank you. All right. Well, if there aren't any questions, we'll move on. But if any questions show up later, please let me know. All right. So we will look at the following map. When I'm going to write gamma, I'll mostly understand through that SL2Z. For the phi congruence subgroups, we'll have different notations. So if you see gamma, think of SL2Z, although occasionally, I think later in the talk, we'll switch to PSL2Z because it will be a little bit more convenient. Okay, let's take K to be this cyclotomic field, all right, the 12 roots of unity, and okay, the ring of integers. So if you consider P to be congruent to 5 mod 12, then right, zeta of 12 satisfies this polynomial, right, this polynomial equals to 0, okay? And for p congruent to 5 modulo 12, this polynomial will factor into 2 irreducible quadratics over fp, which means that zeta of 12, well, the 12th root of unity will actually live in fp squared. And we want that because it seems like in a lot of cases, at least, if you have maps into, for example, FL2, FP, you actually mostly end up, if you take kernels or whatnot, you end up getting like classically congruence subgroups, and we want to look at a class that's classically non-congruence. However, they will be phi congruence for this representation that I'm defining. Okay, so again, we define this representation in 2 different steps. One, we're going to map into SL2OK, and then we'll take a reduction modulo P. So we will map T. So T here, I'm sorry, I didn't write it, but hopefully a lot of you have seen it before. It's just matrix 1, 1, 0, 1. Okay, and we'll map it to zeta. Oh, sorry, this should be zeta 12. So if you're seeing the zeta, it's zeta 12. So zeta 0, 0, zeta minus 1. And then S maps to this. You can see that S squared gives us minus 1. However, an interesting thing is that T usually, right, it has infinite order. However, this T clearly maps to an element of finite order, but everything is all right. It just seems that this map is certainly not injective. But just because it maps to an element of finite order is not too big of a deal, because ultimately we will take reductions modulo P. Okay, so the image of gamma under this homomorphism is given by this set of upper triangular matrices. Okay, and then when we take reductions modulo P, we end up with elements in SL2 FP squared, okay, because this polynomial factors into 2 irreducibles over FP. So again, we have 2 steps. We map a gamma into SL2OK, and then we take reductions mod P. Okay, so one way to get phi congruence subgroups would be obviously to just take these kernels, right? However, these kernels have fairly large index in SL2Z, okay? So we see, sorry, let me just move this, my Zoom thing, okay. So because this has order 12p squared, then it means that the kernel mod P will have index 12p squared in SL2Z, and that's a fairly large index, right? Because we start with p equals to 5, so then we get a subgroup of or index 300, okay? So what we'll actually do, we'll look at some subgroups that contain it, okay? But that's a few slides from now. Before I move on, you may be curious, okay, why are we considering this map at all? And you know how it works with projects that you're working on? You kind of start thinking about things in one way, and it turns out that there's a better way to think about it. So I'm kind of describing kind of like the nice polished version of the project. But at the beginning, what we ended up doing was looking at some maps that were actually taking SL2Z into SL2 OK, where K was totally real. And then it made more sense because we would send T, right, 1, 1, 0, 1 to elements that included fundamental units. And it actually had infinite order. However, looking at some reductions modulo P from that, we've actually noticed these subgroups of order 12p squared. And it was very interesting because then we said, wait a second, these are actually kind of upper triangular, so they're interesting to study. So then we kind of completely modified our representation to be this one, which is certainly I guess it generalizes easier, okay? So for every P, we get this order. For that representation, we got, for some P, we got this order. So if you're curious about why we're even looking at this, it's because we kind of stumbled on these subgroups looking at a completely different representation. And then we figured out, oh, we can get these subgroups in a more mainstream way if we look at this representation. Okay. Now, if we want to understand this particular homomorphism, it will make sense for us to take a little detour to look at the commutator subgroup, okay? So bear with me for a little bit. It will make sense, hopefully, by the end of the slide, why we're looking at commutators. Okay, so gamma prime is going to be the first commutator. Then gamma double prime will be the commutator of the commutator, okay, the second commutator. Some basic facts just about commutators. If you have a G contained in gamma prime that contains gamma double prime, you'll get something normal in the first commutator, okay? You can also remove one prime from each and you'll still get something true, right? So any G contained in gamma that contains gamma prime will be normal in gamma. So this is just a general fact about commutators. However, here we look at commutators of the modular group. So some special facts about that is that the first commutator is free, generated by two matrices. Okay, so this is the A is the commutator of S and ST. So ST is just the order 3 matrix that you might have seen either as U or R, depending on which sources you learned modular forms from. Okay, and then B is the commutator of these two elements. So then gamma prime is free, generated on these two elements. It also has index 12 in gamma. In fact, it is a congruence subgroup. X of gamma prime, so the modular curve, has genus 1. And because it has genus 1, hopefully you can think, oh, wait a second, then you get an elliptic curve. So we will use that geometry to study modular forms for the family that we'll introduce a little bit later, okay? But this will be very important for later on. And then going on to the second commutator, this is free group, but it's actually, it has countable rank. So in fact, gamma prime modulo gamma double prime gives us z squared, okay? So basically gamma prime, very nice, very easy to study. Gamma double prime looks like a bit of a mess. And then you look into like the third commutator and you really probably don't want to be there, okay? So what we will look at are nice subgroups that are contained between gamma double prime and gamma prime. Okay, so a bit of a spoiler alert for later on. Now, to bring back to that homomorphism that we defined earlier, in fact, gamma double prime is contained in the kernel for each prime P, okay? And it will actually be equal to the kernel of the original homomorphism phi, which actually turns out to just be the intersection of the kernel of phi of P, where P is just congruent to 5 mod 12. So basically, you end up with gamma double prime, okay? Then you get the kernel of phi sub P, where P was nice, congruent to 5 modulo 12, okay? And then you get on the other side gamma prime. So the class of subgroups that we'll look at will be contained in between this gamma double prime and the gamma prime. Okay, so I guess I still have to give some two facts that we looked at for this particular representation. So from our previous discussion, we have an exact sequence, okay? So we get gamma, maps into the image of phi, and then the kernel was gamma double prime. What turns out is that the image has the congruence subgroup property, which means that pulling back, we get that the finite index subgroups containing gamma double prime will be the phi congruence subgroups for our representation. So basically, everything in between gamma double prime and gamma prime, as long as they're finite index in our SL2Z, is fair game in terms of phi congruence subgroups. Okay, so this is kind of just the theoretical framework that hopefully will motivate why we're looking at the following family. Okay, so from now on, I'm just switching it slightly. Our gamma is not SL2Z anymore, but it will be PSL2Z. Okay, so I think gamma prime in SL2Z had index 12. So now we get index 6. And then the family of subgroups that we'll define will be the following. Okay, so the gamma prime, it just means that it's contained in gamma. Okay, and then the n will correspond to a certain level. So what we have is that it's going to be the subgroup that's generated by a to the n. So a was that element defined in terms of the commutator of like s and st, and b was something similar. So we take a to the n, b to the n, and then gamma double prime. So obviously, gamma double prime, the second commutator, is contained in these subgroups. Okay, and clearly each gamma prime of n is also contained in gamma prime. So from our previous information, we end up with a finite index subgroup, okay, that's exactly in between these two commutators. And each of these subgroups is phi congruence, okay? So for each n greater or equal to 1, we get these phi congruence subgroups. Why are we looking at this family? We have two kind of main reasons. So the first one is that, yes, we get a family of phi congruence subgroups. However, most of them are classically non-congruence, okay? So if n is greater than 2, all of them are classically non-congruent. The second reason why we're looking at this is, remember our gamma prime, the modular curve x gamma prime was an elliptic curve, right? It had genus 1. Each of these modular curves is also has genus 1. So again, you can think of them as elliptic curves. And we, in fact, will get these tall covers. In fact, there will be, you can think of them in terms of isogenies of elliptic curves that will allow us to study the modular forms for this family. Okay? So with this, basically, if we can understand the modular forms for gamma prime, we can use the geometry of these covers to study the modular forms for gamma prime of n. This modular curve is fairly well understood, okay? So some facts, and I think all of these might have been known by Newman, or actually Newman studied just the modular, just the subgroup, but all of these facts are known in the literature. The modular curve will have no elliptic points, has a unique cusp of width 6, and, okay, of course, has genus 1, we've already said that, but we know what the modular forms for gamma prime look like, okay? The graded ring is generated by the Dedekind eta function to the 4th, E4 and E6, okay? So this is weight 2, and then we have a modular form, the Eisenstein series of weight 4 and the Eisenstein series of weight 6. An affine model for the modular curve is given by this Weierstrass equation. So if you think of x as this modular function, e4 over Dedekind eta to the 8th, okay, so this has weight 0, y has weight 0, you can check that this equality is true, and this is the Weierstrass equation for this modular curve. So the idea is that now we'll take those gamma prime of n, the family that we introduced before, and they will give covers for x of gamma prime. We'll get an affine model for those curves, and then we will use maps from x of gamma prime of n into x of gamma prime, and we'll study the modular forms for the family. Before we do this, just some basic facts if you end up with a subgroup between double prime and gamma prime, okay? So this is the case for the family that we introduced before, okay? Our gamma prime of n are finite index. And indeed, the modular curves will have no elliptic points. All cusps will have width 6. We'll still have genus 1, and then we'll get a cover. In fact, you can think of that cover as an isogeny of elliptic curves. Okay, let me check how I'm doing. Okay, I'm doing on time pretty well. Excellent. So let's talk about those maps. In fact, we have a very familiar affine model for these new modular curves, okay? So I'm putting it a tilde here because the x and the y, so the modular functions that we start with, will not be the same as for x of gamma prime, okay? So for x of gamma prime, x was Eisenstein series e4 divided by eta to the 8th, and then y was e6 divided by eta to the 12th. Because we have a cover, the modular functions for this family will be a little bit different. One way to understand this is to look at the multiplication by n map. Okay, so we have a cover, and then we have a multiplication by n. And basically, we want to get from x of gamma prime of n to all of the points on this modular curve. This notation can look a little bit daunting, but basically each of these are polynomials. They're called division polynomials. They're defined in a lot of classical texts, so you can look at Silverman's Introduction to Elliptic Curves, but basically they're kind of defined recursively, okay, in terms of this C, I think. And these division polynomials allow us to very explicitly think of the multiplication by n map. All right, so what we will do is that we'll solve for modular functions for gamma prime of n by solving equations. Okay, so when I'm saying solve for Q expansions, because the cusps have width 6, this Q isn't like the e to the 2 pi I tau, is actually e to the 2 pi I tau over 6, okay? So I forgot to write that, but basically the Q is e to the 2 pi I tau over 6, okay? And if we want to solve for x tilde and y tilde, well, we basically solve equations given by this multiplication by n map, right? So you basically want to take x tilde and y tilde to x and y on our original modular curve, okay? And then x was e4 over eta to the 4th, and y was e6 over eta to the 12th. So we just have two equations to solve here. Now, each of these phi sub n is very explicitly, can be calculated explicitly because these division polynomials are defined recursively, okay? So I'm going to show you, basically you can just put it in magma. Like, I think that's what we did to get the forms themselves for some small n. you know, you can just put it in magma, it will give you the Q expansion. So these are, you know, the X tilde for small n. Okay, so I'll give you a few seconds to look at this table. Do you notice anything interesting? You can either tell me or just tell yourself if you're noticing anything interesting. Okay, well, for n is equal to 2, you might notice that all the coefficients are integers. And that is not surprising. I said this a little bit before, but if you missed it, we said that for n greater than 3, you end up with noncongruence subgroups, right? Gamma prime of n for n 3 or greater is noncongruence. But for n is equal to 2, we actually get a congruence subgroup, okay? So indeed, all of these coefficients are integers. If you're looking at 3, 4, and so forth, you'll notice that the denominators start growing, okay? And in fact, you can't really multiply any of these forms by any large integer to just get integer coefficients, right? So you get unbounded denominators in that sense. Okay, if you were to get a table for y prime, oh, sorry, tilde y, you'll get something very similar. Now, the other thing that you might notice is that although that's not as easy to check, right? But see if you can notice something about the denominators, okay? What primes show up in the denominators? So for 3, we get a 3 here, okay? 81, so we have a 3 in here. There's a 3 in there too. Okay, cool. Then here, we get a 2, right? For 5, we get the 5. For 6, we get a 3, but notice that we don't get the 2, which is interesting. Okay, so you can kind of like keep going. And just by looking at this, you might notice that, okay, it seems that if an odd prime divides n, that prime shows up in the denominator. So let's look at like 15. Like 3 shows up here, and so does 5. However, if 2 divides n, but 4 does not, you notice that 2 doesn't show up there. Okay, so 6 here, 2 divides 6, but 2 is nowhere here in the denominators. However, if 4 divides n, then 2 does indeed show up in the denominator. Okay, so for 4, we get 2's in here. For 12, we get 2's in here, etc. So looking at this, we wanted to see, can we tell more about what primes show up in the denominators? And indeed, just this observation turned out to be true. Okay. Basically, just kind of like a basic observation is that the Q series had coefficients in Q. However, if we have a prime co-prime to our level n, then that prime does not show up in the unbounded denominators. Okay, and actually you get that the Q series is L integral. However, if P is an odd prime dividing n, it shows up in as an unbounded denominator. However, if P is 2 and 4 divides n, then it shows up as an unbounded denominator. So basically, if just 2 divides n, but 4 does not, it doesn't show up there. I'm not going to tell you exactly like all the steps and how we arrived at this, but the general idea, and if you excuse me, I'll move a couple of slides earlier, we used these division polynomials. So basically, we kind of did some Hansel's lemma lifting to show first that if we have a prime co-prime to n, then it doesn't show up in the denominators, okay? And then we looked at primes, at powers of prime that divide n. So basically, we kind of just did it recursively in a way by Hensel lifting. So it's very explicit. Now, what I'm not going to say too much is that specifically for p is equal to 2 and p is equal to 3, we don't just get that it has unbounded denominators, but we also had some bounds on the power that shows up. Okay, not so much for the other primes. Okay, basically, we have the modular functions that generate the function field. So hopefully we can say more about the modular forms. But it looks like I'm going very fast through everything. So are there any questions? Okay, well, we would have liked to say something more specific about these families. And in fact, we do have a result on the primes that show up not just in x tilde and y tilde, but also in the modular forms. And there are some fairly well-known ways to get a dimension formula, right? Because we know for gamma prime of n, we know the number of cusps, we know the number of elliptic points, etc. So we can get a dimension. We can get a dimension formula for the modular forms as well. However, we weren't too successful getting very specific generators. However, we got, at least some presentation for the modular forms. So basically, all the modular forms of even weight for our family have the following form. So this is one of the division polynomials. Okay, we get eta to the fourth. So I think what we end up here. So I think the divisor for this is just the is just infinity. Okay, so it cancels out with eta to the fourth. So you end up, so all the divisors kind of end up canceling nicely, and you get a honest to God modular form. Okay, so homomorphic, right? So we have bounds on the degrees for these polynomials. However, it would have been interesting to get, can we say anything more specific about the generators for like a given weight, right? Or maybe generators for the graded ring. But based on this presentation, we can say about the primes showing up in unbounded denominators. Well, it's kind of like it's an easy corollary from the information that we know about x tilde and y tilde. So specifically, unbounded denominators show up at odd primes dividing n, okay? Or at 2 if 4 divides n. So very similar to our previous setting. And moreover, so basically all the information that you need to know is from x tilde and y tilde. Okay, so I want to end the talk with actually a family that we considered before this one, but unfortunately we weren't able to tell too much about it. So we just kind of went back and focused on this family instead. If you're taking phi to be our initial representation, okay, so you'll remember that the image mod p was actually in SL2 fp squared. So I think you had u to the 12th was equal to 1, okay, and then v was in fp squared. Now, take instead the pre-image of this subgroup. Okay, so v is now in Fp, and then you have u to the 4th is equal to 1 as opposed to u to the 12th. These subgroups now have index 3 times p. So the index is way nicer than what we had just for the kernel, which I think was 12p squared. So at least for p is equal to 5, I think we get index 15, which is pretty cool. And in fact, we managed to look at the sum for G5, and we get something that's fairly nice. I tried to draw, so I think this design was actually given, was made by one of Cam's grad students, Alan Stokes. He's doing a lot of things with Bailey maps. But then if you're trying for G17, right, also 5 mod 12, you end up like getting a lot of loops happen, like kind of growing from this part, okay? So this is kind of like the nicest example. Initially, we wanted to say more about the modular forms for these GPs. Because the index is 3 times p, we're hoping to get like very nice generators, but we kind of got stuck there. However, the methods, similar methods to what we talked about earlier, now taking gamma prime intersected with GP will basically give us, right, those subgroups between gamma double prime. Okay, so these tilde GP are in between gamma double prime and gamma prime, finite index, so they're phi congruence, and we can actually also use geometry now with gamma tilde to study modular forms for these G tilde of P, and then kind of come back to the GPs, okay? So the GPs are noncongruence of index 3 times P. And we can say more about the number of cusps, okay? So we have p plus 1 over 2 cusps, 3 elliptic points of order 2, no elliptic points of order 3, and then we can use the genus formula to get genus 0. So these groups would be very probably easy to study, but we kind of got stuck trying to get generators for the graded ring, but I think it should be doable. And I forget what I wanted to say for the very last thing, but basically I think studying this subgroup, these groups, because they have such small index, could probably give some nice graded rings. Okay, I guess I'm a little bit done a little bit early, but this is everything that I have today, and please let me know if you have any questions.
So, any questions in the room or in the chat? I do have too many anyway, so. No, please. Yeah.
I have a question, but a quite general one, just about as you see, you construct groups which are of finite index and not congruent subgroup.
So, these guys?
Yes, for instance, or just before you see the one you introduced with the phi.
Ah, okay.
I guess my question was just quite related to the congruence subgroup problem. But I don't know if you thought about it or just how does it behave? Like Z, when you take SL2 of Z, you can take the completion by all of finite index subgroup, and you want to compare this with SL2 Z hat. Like just you cut over, you take the completion over just congruence subgroup. So I don't know if what you may obtain if you take instead of the completion by a congruence subgroup by your congruence phi subgroup.
Oh, yeah, I don't know. So for a different family, and I think in that case we had phi mapping into like as a symplectic representation. In that case, we had a surjective homomorphism, and we managed to actually lift surjectivity mod P to surjectivity in ZP, so in kind of the completion. So if I'm understanding correctly, is that I think because we're taking things modulo P, in some cases at least, we should be able to even move on to like SL2 ZP, but I don't know about a general theory. For so far, we can just do it kind of like case by case. I mean, this one is obviously not surjective, but right, like we only get upper triangular things. But I think depending on the examples, we might be able to tell more.
Yeah, thank you.
Thank you.
Further question? Comments? So, questions are when you have a case where you could have several phi, so how could you compare the different representation depending on phi?
Oh, so that's very interesting. So one of the things that we kind of thought about, not too much, but that would be interesting to think about, I guess, a little bit more, is, right, so Will Chen's work gives, moduli spaces of elliptic curves with non-abelian level structures for non-congruent subgroups. And it would be interesting to say, okay, for how do these level structures, what do they have to do with the image of phi? And I think there is a connection between that and like the image of phi, but the connection is not super clear. So at least that we should be able to do that for like specific phi. So for like this one, maybe we can look at what sort of level structures do we get for those moduli spaces. But it'd be interesting to get to a more general theory. So to kind of answer your question, okay, how did things compare with different representations? We don't know. It's very interesting. We wish we could know, but that's for the future.
And okay, so maybe a more difficult question. Sorry, can we expect to do the Scholl method? The global Scholl method with the non-congruence subgroup.
Oh, sorry, can you repeat that?
The Scholl method, I mean the Tony Scholl method for King's-Wheaton Dyer. So which use a motivic approach. So could we expect to do the same thing here?
No idea. I mean, we can hope, right? But we don't know yet.
Because most of the parts are quite, I mean, it's you have a machinery, you have the definition, let's say, I mean, the definition that you propose seems at least should be compatible in parts at least.
Yeah, I'm interested in a lot of the like the ASD congruences and like
yes,
I guess
yes.
the representation that we get, right, the Scholl representations can tell us a lot about that. So I don't know. I'm curious, but we don't know yet.
And my last one, do you have an example with SL3?
We didn't look specifically at SL3. I mean, actually, I'm lying. We did look at one example. We just somehow decided to prioritize the symplectic. So I didn't talk at all about the symplectic representation that's in our preprint, but I think, I mean, there's ways to create something fairly similar for SL3, but I just can't remember the specifics of that example.
Okay. Thank you. No more comments in the chat or in the Zoom chat. No. So thank you again.